Okay. Today we will see the data encoding and communication techniques. Okay. So what is encoding? We have to transfer the data. We have to communicate the data from receiver to, sorry, from sender to receiver. That is the encoding. It must be, it is not directly that you are passing the message from one to the other. That is not easy in terms of what digital or data communication. We must what convert that data into some meaningful format. Then only it will be transferred from machine to machine. So for the transmission purpose, we require the data must be encoded. So what is that encoding? So encoding is the process of converting the data or a given sequence of characters, symbol, alphabets into a specified format for the secure transmission of data. Means we are what inserting some signals, clock, high voltages for what secure transmission of data. So encoding is done at the sender side. Now receiver, what will be the role of receiver? Receiver is responsible for decoding, that is separating clocks and data from the incoming embedded stream. Okay, so what we are doing some conversion over the data for secure transmission, and receiver will what filter out that conversion. Okay, he will take the data only for the further process. Systems that use encoding are synchronous system, and we must encode data into signals to send them from one place to another. That data transmission is important in the case of what data communication. So what are the different possible? Now you know there are two types of signals we have seen. We have to transfer the data into the form of signal. Now there are two types of signals. We have seen what analog and digital. We have seen the difference, that is the analog in the waveform and digital is in the these types discrete format. So this transmission is what will be possible. 2 raised to 2 means what? The four way. That is digital to digital, digital to analog, analog to analog, and analog to digital. So these techniques we have to learn in this chapter, that how we will transfer the data from digital to digital signal. Means what? We are transferring the data from the what digital signal to again digital form. Digital form. Signal, you can remember that signal digital means what? In the square form, where and analog means what? In the wave form. Okay, so what will be digital form means what? 0 1 format. Okay, so digital to digital conversion is what? Somewhat simpler. We have to convert the binary signals. Okay, and we have to insert the sequence of voltage pulses that can be sent through the transmission medium. The binary signals created by the computer are translated into a sequence of voltage pulses that can be sent through the transmission medium. Now it has the basic parameters, amplitude and duration. Amplitude, it has only two amplitudes, two states, 0 and means that is the off, or on means what? The one stage. Okay, so the process of converting binary ones and zeros created by a computer into a series of voltage pulses that can be transferred across a wire is known as what? Digital to digital encoding. Okay, so binary, what is that? Amplitude means what? 0 means what? Off stage, and 1 means what? That is the on stage. It has only two states of amplitude. And duration means the time between what? For transferring that signal. As the number of bits sent per unit of time increases, the bit duration decreases. Okay. The three most common methods of encoding used are what? Unipolar, polar, and bipolar for the digital to digital encoding. So we will see means what from the 01 format to the again 01 format, but we are inserting some high voltage signals for the transmission. So we will see this unipolar, polar, and bipolar. So this is the line coding means what? Digital to digital is also called as what? Line coding 010 format into this C script to the this digital format. High voltages are there, which shows that first is 0, then 1, then blank, then 1. Like this, we are transferring the signals. So what is unipolar encoding? So we can see a signal with the DC component and a signal without the DC component. Now, the simplest and the most primitive type of encoding is unipolar encoding. Digital transmission. What we have learned? We have learned that what digital to digital means we are sending the voltage pulses over the medium such as wire. Okay. So typically one voltage level stands for binary 0 and another voltage level for binary 1. Polarity refers to whether you have a positive or negative pulse. Example means what? 1 is used for what? Positive high voltage and 0 is considered as a 0 voltage. So from the figure, okay, it's not clear from the figure. We will go into the detail. What is that unipolar encoding? We are using a positive 1, means this one for the positive voltage. Okay, and 0 volt indicates a binary 0. Unipolar encoding uses only one polarity, only one of the two binary states is encoded, usually the 1. Okay, so when we are transferring the data with this unipolar encoding, it is in the form of what? 0 and 1 means what? On and off stage. Okay, 0 represents the off stage and 1 represents the on stage. We can what? Convert the digital signals into the digital itself with the high voltage pulses. Two problems with the encoding DC component and synchronization. Okay, 0 1 format we are using for 1 is for what? On stage and 0 is for what? Off stage. This is the unipolar encoding. The diagram is not, I think, in your book. This is just for your understanding. Okay, so this is what unipolar encoding from the sender side. Now problems is what? DC component. DC stands for the direct component. Average amplitude of a unipolar encoded signal is non-zero. Okay, this creates a direct current, shifts the zero level that cannot travel through some media, example microwave. Amplitude is what? Non-zero. so which creates a direct current. You can skip this slide as this unipolar just definitions are right there, and synchronization between the sender and receiver must be done for the easier transmission of the data. Okay, this if there is lack of synchronization, the signal is sent across and received. We can see the how it is received. You can see it's 111. Okay, there is only two ones are there. Here it is receiving again. If the time is two, synchronization means it has started late, then it will receive one extra bit here. So there is what, due to lack of synchronization, the signal or the data sent may be the same. Okay, or we may receive the data with some errors. So that is the problem with the unipolar. Now next, what is the polar scheme, polar encoding? Positive and negative amplitudes. Two voltage levels, positive and negative of amplitude. Okay, it eliminates some of the DC residual problem because the average voltage level on the line is reduced. The power of to transmit the signals is one half of that of unipolar signal. That is NRZ, RZ, Manchester, and differential Manchester. These are the different polar scheme. Okay, what is NRZ? Non-return to zero. Okay, and RZ means what? Return to zero. This is in the terms of what? Signal encoding, polar encoding types are there. How we are using this encoding. Encoding means what? We are, again I am back to the definition, means what? We are converting the data with the voltage levels. Okay, just we are using in the digital to digital two voltage levels. One is positive and one is negative. Okay, so in the polar encoding we are using the different, that is non-return to zero, return to zero, Manchester, and differential Manchester. It uses the two voltage levels. Okay, so non-return to zero, this is the signal is always positive or negative. Positive, just remember the signal may be positive or negative. Non-return to zero signal, we have to write in terms of what? 0 and 1. Non-return to zero. Sorry. So two main types, NRZL and NRZI. Again, we are what? Classifying this non-return to zero into two types. So what is NRZL? Signal never returns to zero voltage and the value during a bit time is a level voltage. Non-return to zero L, NRZL. So what is that NRZL? Signal never returns to zero voltage and the value during a bit time is L for the level voltage. If you know the voltage, we are using the voltmeter in our fridge, means what? We are converting that signal, electronic signal, into a specified voltage which our home devices are using. Okay, so this is good for short and well shielded transmission paths. In NRZ, the level of the signal is dependent upon the state of the bit, dependent upon the state of the bit. Okay, I have repeated again, repeat the same. Depend on the state of the bit. Now see what will be the state of the bit in the digital transmission. It may be 0 or it may be 1. Okay, remember this is non-return to 0 L. L stands for the level voltage during a bit time, means 0 and 1. It is particular level, one of the level of the voltage is determined. And NRZ I invert on ones, non-return to 0 inversion, invert on ones. Okay, what is, you know, the inversion? What do you mean by the inversion? Means what? We are what? Inverting into the, means what? The reversal state. Reversing something, that is we are called as the inversion. Okay, so the transition between a positive and negative voltage represents a 1 bit. Okay, 1 bit voltage, the transition between a positive and negative voltage represents a 1 bit, provides more synchronization than NRH because there is a transition for each 1 bit. In NRZI, the signal is inverted if a 1 is encountered. If there is 1, the signal is what? Inverted, means it is, again it is converted to 0. So that's why it is called as the invert on ones, means each time the transition, the difference we are representing with the help of 1 bit. Okay, so this is the non-return to 0 inversion. NRZL, that is that simply it is what going, but NRZI inversion, see how it is transition, because next bit is what? 1. So it is what becoming the 0. See, like this. This is the regular our non-return to 0 level. Some that this voltage level is achieved here. Okay, here again returning to 1 to 0, because what? Next bit is what? 1. So it is returning to the 0 state. 1, then again we are returning to 0. Again 1, then it is returning to, from this returning to 0. So like this we can represent the signal. Next is the RZ encoding. So what is that? It tries to solve the problems of losing synchronization due to a long strings of consecutive ones or zeros. See, there are long strings of zeros and ones. We are seeing the less amplitude here. The distance is less here. Signal change during each beat promotes synchronization. Positive voltage 1, negative voltage 0. Signal returns to 0 halfway through the beat interval. These transitions can be used for what? Synchronization between the sender and receiver. See, from the diagram we have to write. Now what we are learning? Digital to digital transmission. We have seen the different techniques. In this, RZ encoding means what? Return to 0, where what? Signal drops to 0 between each pulse. Okay, means intermediate, it is not covering the whole pulse, it drops to 0. Again here it is what? 0. It again what? Changes is transition 1, means between this it changes its position. So that is called as what? Return to 0. In previous one, we are seeing the signal directly from this to this or from this to this. Here in between, the signal changes the its states. So that is called as what? Return to zero encoding. Binary low and high pulses. So which will be better? Okay, if we are changing the state continuously, so RZ is not actually better way for the encoding medium. Hmm. So next is the biphase. Signal changes at the middle of the bit interval, does not return to zero, goes to opposite pole. Good solution to synchronization problem. Two types of biphase encoding used in networks: Manchester and differential Manchester. Okay, Manchester encoding. We will see what is that Manchester encoding. This is not the Manchester Football Club. We will see the Manchester encoding. This code is what? Self-clocking Manchester. I will see with the help of diagram. We can see what is Manchester encoding. In Manchester encoding, the transmission at the middle of the bit is transition at the middle of the bit is used for both synchronization and bit used for both synchronization and bit representation. What in this encoding, the data bit is either what? Low, then low, then high. Okay, zero is what? This is the zero. And one is this. So the data bit is either low, then high, or high, then low for equal time. Okay, there is no means what? Variable time is not there. Either that both low to high and high to low is at the same time or equal time. This is most important feature of this Manchester encoding. You have to draw this diagram and we have to what? Explain. It is a self-clocking signal with no DC component. Okay, self-clocking 0 1 0 0 1 1 0. This is the time, this is amplitude. Okay, and this is the Manchester encoding. We can represent with the 0 with this and 1 with this. Okay, so synchronous clock encoding technique used by the physical layer of the OSI model. We have seen the OSI model. Okay, one logical state means 0 from one state to the other state with the same time interval. That is the Manchester encoding. When we are using this with the Ethernet LAN, we are using the Manchester encoding techniques. Next is the differential Manchester encoding. So differential Manchester means for presence of transition at the beginning of bit time means the 0. Transition of every bit in the middle of the bit cell. Differential Manchester in the middle of the bit cell. Okay, transmission at the beginning of the bit cell if the next bit is what? 0. No transition at the beginning of the bit cell if the next bit is what? 1. Okay, see, there is what? If the next bit is 0, then the transition is taking place. If the next bit is 1, there is no what transition, means the signal is not dropped to 0. It remains the same from 1 to 1. That is the differential Manchester encoding used in token ring or IEEE 802.5 complement LANs. Okay. The transition at the middle of the bit is used, transition at the middle of the used only for synchronization. The bit representation is defined by the inversion or non-inversion at the beginning of the bit. Means according to the next bit, we are what encoding the data. That is what differential Manchester encoding, and where we are used in the token ring or IEEE 802.5 complement LANs. So this is the difference between the regular Manchester and the differential Manchester. Next form is what? Analog to digital encoding. So this is the analog signal. This is the amplitude. Pulse amplitude modulation signal. This is what pulse amplitude modulation signal from what? Analog to digital. The challenge is to transform potentially infinite values in an analog message to digital without losing data. Example, voice on the CD. Means what? We have to transfer this signal in the format of what? Digital signal, means 0-1 format without losing the data. Like if we are transferring the data or the video, the background voice must be there. Okay, so this is what the main feature, means what? In the data communication we must not lose the data, otherwise only film will be there and no voice, then there will be problems. Means we lost the meaningful information. Whatever the goal, whatever the media, whatever the technique we are going to use, we must save our data. We must not lose our data. Okay, that is the main theme behind this what? Encoding technique. So analog to digital encoding. We have to convert these analog signals into the digital form without losing any important feature. So first method is what? Pulse amplitude modulation, that is PAM. Okay, samples the analog message and generates pulse based on the sampling. Sampling measures the amplitude of the signal at the equal interval. So see, here we are seeing the amplitude is this only. So the pulse is this much. The amplitude is higher, the pulse is also more here. The analog signal amplitude is like this here, so its PAM signals pulse will be also like this. So we have to what? Generate the pulses, pulse code modulation. Okay, we have to convert these amplitudes this into the pulse amplitude modulation, that is the PAM. This is the most common technique. So PCM encoder, we will see the PCM in detail, uses 3 to 4 processes to create a digital signal. Sampling, quantization, okay, binary encoding and digital to digital encoding. Highest frequency sampling rate equal to 2x sample per second. Sampling intervals means what? The difference between this to this. This is the Nyquist theorem. PCM is the sampling method used to digitize voice in T-lines transmission in North American telecommunication systems. Okay, So this is the amplitude. This is that above the previous diagram signals pulse code modulation is given here. Okay. So PCM sampling rate twice the highest frequency of the original signal to ensure the accurate reproduction of an original analog signal using the PAM. The first step is sampling. What sampling is, what means what? Process of measuring the amplitude of a continuous time signal at the discrete level. Okay, so we are measuring, we will see this is somewhat, it is actually sampling with what, measuring the distance between these two, and then we are generating the pulses according to this. This is the sampling of the signal. And what is that, this Nyquist theorem? So this is what sampling rate, the Nyquist theorem states that sampling rate, or about the sampling rate or the frequency. The sampling rate must be at least 2 times the highest frequency contained in the signal. So it is called as what? Fs equal to 2 into Fh. It is also known as the minimum sampling rate. So this, the Nyquist theorem states that the sampling rate must be at least 2 times the highest frequency content in the signal. Highest frequency, if this is x, then the sampling rate must be 2x samples per second. This is the Nyquist theorem in the pulse code modulation. Okay, PCM sampling rate. We have to draw this diagram, and we have to write this Nyquist theorem also. I have given in short for the better understanding. We will see the next part after this slide in the next recording.